Okay, group 7, the halogens. Now, I don't want to spend too much time doing the really basic stuff. Of course, they all exist as diatomic molecules. So this is a, I've never seen it because I think it's very hard to have enough of it to see because it's very difficult to work with. Apparently, it's a pale green gas or pale yellow gas. Chlorine is a greenish gas, room temperature. Bromine is a fuming red-brown liquid. Iodine, I think boiling point of that is 59 degrees C, so it gives off a lot of fumes at room temperature. Iodine is a black solid. It sublimes at atmospheric pressure at about 110 degrees C into a lovely purple vapor. Iodine is always a bit confusing because you probably come across it in biology as like a brown solution. Iodine itself is not very soluble in pure water, but you can make it dissolve in potassium iodide solution. What happens is, so you get your iodine molecules, there's an equilibrium reaction and they form I3- ions, and these are the ones that are brown. They're like a brown color in solution. So normally when you have a bottle of, when you have iodine, what you've actually got is your little iodine bottle you used to test the starch in biology. What you've actually really got in there, you've got I2 in potassium iodide solution. And that looks that sort of brown color. Okay, why do the boiling points increase as you go down? Well, that's because you've got van der Waals forces in those pure liquids, haven't you? And they get bigger as you go down as the molecular weight of the diatomic molecules increases. So, as I say, that's kind of not very difficult stuff. So, let's move on to the more important trends. Okay, now we know, right, that all halogens they have 7 electrons in their outer shell, and so they tend to form -1 ions. Okay, so you have the F-, Cl-, Br-, and I- ions. They are usually called the halide ions collectively. Right, and they all have that tendency to gain. They've all got 7 electrons are out of shell. They all want to gain 1 and form this ion. Now, if you think of it as a series of little equilibria, so I've got chlorine has a tendency to accept. I'll do fluorine first. Sorry. Okay. Fluorine has a tendency to accept 2 electrons to form the fluoride ion. So does chlorine. So does bromine. And so does iodine. So let's think about those little equilibria there. Right, so let's look at fluorine. Fluorine is a small atom. It's got a great tendency to accept an electron and become a fluoride ion. I hesitated to use the word electronegativity here because electronegativity, of course, refers to an ability of an atom to draw electrons towards itself in a covalent bond, and we're not talking about covalent bonds here. We're talking about forming ions. So I'm not going to use that word electronegativity, but fluorine has got a very strong affinity for electrons. Okay, so this equilibrium is very far to the right. Now, chlorine is not quite as good at attracting electrons as fluorine, because of course chlorine, it's got a bigger nuclear charge, but the electrons that it's got to attract an electron into that third shell, so you've got shielding and greater distance from the nucleus. So chlorine is not quite as good as attracting as electrons as fluorine. Likewise, bromine is slightly less good still, and iodine is the worst of all, okay, at doing it. Right, now we need to think about oxidation and reduction here a lot when we're talking about the halogens. Okay, now these species here, the halogens, they're all potential oxidizing agents. Why are they potential oxidizing agents? Because they've all got a tendency to become reduced themselves by accepting electrons. Now, who's going to be the best at accepting electrons? Fluorine, chlorine, bromine, or iodine? It's obviously going to be fluorine. So that is so I'm going to draw a little arrow here. Increasing strength. Well, let's just say best oxidizer. It's quicker to write. Best oxidizing agent. So iodine is the worst oxidizing agent. Right, now on this side here, these ions, these are all potential reducing agents. Why is that? Because they have some tendency, to give away electrons, okay? And as we've seen, fluoride ions have got virtually no tendency to give away electrons. So they're very poor reducing agents. Iodide ions, on the other hand, they've got a reasonable tendency to do that, so they are not bad as reducing agents. It's not that strong. So I'm going to draw a blue arrow here and say best reducing agent. Now, if you're in year 13 and you're looking at this, you probably want to look at, I forget what number it is, I think it's 1.11 electrode potential topic. You want to look at that. Have a look at that. It will make some sense. I don't know the standard electrode potential. So, but if you're in year 12, don't worry about that. Okay, so let's have a think about some halogen displacement reactions, which you have done in you've done that in year 11, but let's have a look at it now. So halogen displacement reactions. So if I got a beaker of potassium iodide solution, which of course is colorless, and I add some chlorine water to that, so Cl2, that's in aqueous solution. What happens is this solution, it turns brown. Why does it turn brown? Well, you've formed iodine in there. There's been a displacement reaction. So let's have a little think about what's going on there. So let's write an equation for it. So write an equation, we write down Ki, right, and I can't stress enough, that is colorless, it's not brown. Just like KCl is colorless, it's not green because it's got chlorine in it. KBr isn't brown, that's colorless as well. When the halide ions are not colored. Okay, so that's going to react with some with chlorine water, sorry. And we're going to get KCl and I2. Just balance that, okay? So we can actually rewrite that as an ionic equation. It will make more sense. So we're going to end up with I minus, 2I minus. The potassium ions are spectator ions, I'm going to leave them out. Cl2. And it goes to 2Cl minus, potassium spectators, and I2. So we can see all that's happened there really is that the iodine has become oxidized because it's lost electrons. And the chlorine has become reduced because it's gained electrons. And we could write that down as two half equations. So the two half equations, which we've actually got up there already, haven't we? But I'll just write them again. So we've got 2I minus goes to I2 plus 2 electrons, and the chlorine Cl2, 2E minus goes to 2Cl minus. And of course, where those electrons are coming from, these electrons get passed on to there. So it's like a competition between the chlorine atoms and the iodine atoms. Who wants the electrons the most? And the chlorines want them more because they are, the chlorine atom is, draw a little, there's your chlorine is small and your iodine is bigger. So the chlorine has got to attract the electron into this shell here, which is closer to the nucleus, and it hasn't got as much shielding. Iodine has to attract it, it's a much bigger atom. Do it there. Okay, so that explains halogen displacement reactions, and also we have a look at this, and you can see, right, if you tried to react, let's say, if you added bromine water to chloride ions in solution, no reaction there, because the chloride ion is better at holding on to the electrons than the bromine is, so no reaction there. If you did it the other way around, it would work. If you added chlorine to solution of bromide ions, potassium bromide, the chlorine would take the electrons off these bromide ions and become reduced to the chloride ion itself and oxidize the bromine to Br2. So that's all fairly straightforward, and to a large extent you touched on that at GCSE. But this idea of thinking about these as oxidizing agents here, and these as reducing agents is quite useful. Incidentally, you would never do displacement reactions with fluorine, because you can have chlorine water, you can have bromine water, and you can have iodine dissolved in water. You can't have fluorine dissolved in water, because fluorine is such a good oxidizing agent, it will rip the electrons off the water, and it won't just dissolve, it will form fluoride ions. So you can't have fluorine water. And anyway, no one does any experiments with fluorine because it's very reactive and dangerous. Fluoride ions are very poisonous. I think fluorine was the last halogen to be isolated, and I think a couple of scientists died in the process in the 19th century, died in the process of trying to isolate pure fluorine as an element, because the hydrogen fluoride which they're using is very poisonous and killed them, I think. So on that cheerful note, I think we'll end it there.